Hello, everyone. This is Leo Mora, your host for Suntawk, Sundays talks about wisdom and knowledge. In the previous session, we had the topic of fundamentals of quantum mechanics. So we talked about vibrations, waves, frequencies, sound. In this session, we're going to talk about the what follows to that. But before that, normally we have a group of people in these talks, but right now Suntawk it's only like a TV program, so it's just me talking and no audience. So normally we would have no debates, intellectual development for the group, open-minded, good vibes. We want to attain wisdom through knowledge. And with that, we want to have the power. So, the topic for today is the quantum universe. It's a very summarized, and quantum physics is very extremely complicated to talk about. So, I try to make this as summarized and as simple as possible so we can all understand. So, let's begin. So, quantum mechanics is the branch of physics that studies the behavior of matter and energy at the atomic and subatomic levels. At this scale, the world is very different from our everyday experience. For example, particles can be in multiple places at once, and they can even pass through walls. Quantum mechanics is a very successful theory. It has been used to explain a wide range of phenomena, from the behavior of the atoms to the structure of the stars. It has also led to the development of many new technologies like lasers and transistors. However, quantum mechanics is also a very strange theory. It says that the world is not deterministic but probabilistic. This means that we cannot predict the future with certainty, but only with a certain probability. One of the most important concepts in quantum mechanics is wave-particle duality. This says that the particles can behave like waves and waves can behave like particles. For example, electrons can behave like waves when they are diffracted through a crystal lattice. Another important concept in quantum physics is the uncertainty principle. This says that there is a limit to how accurately we can know the position and momentum of a particle. The more accurately we know the position, the less accurately we can know the momentum and vice versa. Quantum mechanics is a very complex theory and it is still not fully understood. However, it is one of the most important theories in physics and it has had a profound impact on our understanding of the universe. So, here are some of the key concepts of quantum mechanics that we are going to see today. Wave-particle duality, uncertainty principle, superposition, quantum field theory or QFT, entanglement, and we will see a little bit of quantum computing and kind of the history. So let's begin. So this is the first of the group that I just mentioned, wave-particle duality. The wave-particle duality is a fundamental concept in quantum mechanics that states that every particle can be described as both a wave and a particle. This means that particles can exhibit wave-like properties such as interference and diffraction, and waves can exhibit particle-like properties like momentum and energy. This concept was proposed by Louis de Broglie in 1924, who suggested that all matter has a wavelength associated with it, given the equation lambda equals h over p, where lambda is the wavelength, h is the Planck's constant, and p is the momentum of the particle. This one idea was later confirmed by experiments such as double-slit experiment, which showed that electrons could behave like waves and interfere with each other. Wave-particle duality is a counterintuitive concept and is as it challenges our classical understanding of the world. In classical mechanics, particles and waves are distinct entities. However, in quantum mechanics, there are two aspects of the same thing. This duality has profound implications for our understanding of the universe. It means that the world is not as deterministic as we once thought. Instead, it is probabilistic, and the behavior of particles is governed by probabilities, not certainties. Wave-particle duality is a cornerstone of quantum physics, and it has been used to explain a wide range of phenomena from behavior of the atoms of the structure to the structure of the stars. It is also the basis of the modern technologies such as lasers and transistors. The uncertainty principle. The uncertainty principle, formulated by Werner Heisenberg, is a fundamental concept in quantum physics that sets a limit on the precision with which certain pairs of physical properties, such as position and momentum, can be simultaneously known. In simple terms, the more accurately you know a particle's position, the less accurately you can know its momentum, and vice versa. This isn't due to limitations in our measuring systems, but rather in inherent property of quantum systems. Particles at the quantum level behave as both particles and waves, and this wave-particle duality gives rise to the uncertainty principle. Imagine trying to pinpoint the exact location of a wave. The more you try to confine it, the more its wavelength and thus its momentum becomes uncertain. Conversely, a wave with a well-defined wavelength is spread out and its position is less certain. The uncertainty principle is mathematically expressed as delta x times delta p, the Planck constant divided by 2. This principle has profound implications. It means that the classical idea of a particle having a definite trajectory is not applicable at the quantum level. Instead, particles exist in a probabilistic cloud of possible positions and momentum. The uncertainty principle is not just an abstract concept, it has real-world consequences, such as limiting the accuracy of certain measurements and influencing the behaviors of atomic particles in various phenomena. Superposition. Superposition is a fundamental principle in quantum physics that states that a quantum system can exist in multiple states simultaneously. Unlike classical physics, where an object can only be in one state at a time, a quantum particle, like an electron, can be in a combination of multiple states. Think of it of a coin spinning in the air. It's neither heads or tails until it lands. Similarly, a quantum particle can be in superposition of multiple states until a measurement is made. These states can be anything measurable, such as position, momentum, spin, or energy. For example, an electron can be in a superposition of being in two different locations at the same time. It's not that it's rapidly switching between the two locations, it's generally on both places at the same time. The superposition is described mathematically by a wave function which represents the probability of the particles being found on each state upon measurement. When a measurement is performed, the superposition collapses and the particle chooses one of the states. This collapse is probabilistic. We can only predict the probability of the particle ending in a particular state, not which state it will definitely be in. The concept of superposition is crucial for understanding many quantum phenomena. Its base is the basis for quantum computing, where qubits can exist in a superposition of 0 and 1, allowing for vastly increased computational power. It also plays a role in quantum entanglement and other quantum effects. While controversial to our everyday experience, superposition is a cornerstone of quantum mechanics and has been experimentally verified numerous times. It highlights the probabilistic nature of the quantum world and the fundamental difference between classical and quantum physics. Now let's take a look at QFT, or quantum field theory. It is a theoretical framework that combines quantum mechanics with special relativity to describe the behavior of subatomic particles and their interactions. It is a more sophisticated theory than quantum mechanics, which primarily deals with particles, while QFT focuses on fields. In QFT, particles are viewed as excitations and disturbances in underlying fields that permeate all space. For example, an electron is a ripple in the electron field, and the photon is a ripple in the electromagnetic field. These fields are quantized, meaning that the excitations can only occur in discrete amounts corresponding to the particles we observe. QFT provides a comprehensive framework for understanding the fundamental forces of nature. It describes how particles interact through the exchange of particles called force carriers. For instance, the electromagnetic force between charged particles is mediated by the exchange of photons. QFT has been incredibly successful in explaining a wide range of phenomena in particle physics. It forms the basis of the Standard Model, which is our current best theory for the fundamental constituents of matter and their interactions. However, QFT is also very complex and mathematically challenging theory. It involves infinites that need to be carefully handled through a process called renormalization. Despite these challenges, QFT remains a cornerstone of modern physics, providing a deep and accurate description of the quantum world. Quantum entanglement. It is a peculiar phenomenon in quantum mechanics that two or more particles become linked together in such a way that they share the same fate, no matter how far apart they are. This connection is not a physical one, like a string tying them together, but rather a correlation between their quantum states. Imagine two coins flip at the same time. In the classical world, each coin has 50-50 chance of landing in either heads or tails, independent of each other. But in the quantum world, if these coins are entangled, their fates are intertwined. If one lands on heads, the other will land on tails, even if they are miles apart. This happens instantaneously, seemingly violating the speed of light, which is why Einstein called it spooky action at a distance. Entanglement is not just a theoretical concept, it has been experimentally verified by various particles like photons, electrons. Scientists have shown that measuring the property of one entangled particle instantly influences the property of the other, regardless of the distance separating them. This has profound implications for our understanding of reality and the universe. One of the most intriguing applications of entanglement is in the quantum computing. Quantum computers use entangled particles to perform computations in a fundamentally different way than classical computers. This could potentially lead to solving problems that are currently intractable for even the most powerful supercomputers. Entanglement also has potential applications in quantum communication. By exploiting the instantaneously correlation between entangled particles, it may be possible to develop secure communication channels that are impossible to eavesdrop. This is because any attempt to intercept the information would disrupt the entanglement, alerting the communicators. However, entanglement is not without its challenges. One of the main hurdles is maintaining the fragile quantum states of entangled particles. They are easily disturbed by interactions with the environment and phenomena known as decoherence. Overcoming these challenges is crucial to realizing the full potential of entanglement in quantum technologies. Despite these challenges, entanglement remains one of the most fascinating and promising areas of quantum mechanics. It offers a glimpse into the strange and counterintuitive world of quantum mechanics, and it holds the potential to revolutionize computing, communication, and our understanding of the universe. Quantum computing is a revolutionary approach to computational that leverages principles of quantum mechanics to solve complex problems beyond the capabilities of classical computers. While still in its early stages of development, quantum computing holds immense potential to transform various fields, from medicine to material science to finance to artificial intelligence. Fundamental concepts. At the heart of the quantum computer lies the qubit, the quantum analog of the classical bit. Unlike a bit, which can only be 0, 1, a qubit can exist in superposition, representing 0 and 1 simultaneously. This allows quantum computers to explore a vast number of possibilities concurrently, providing a significant advantage for certain types of problems. Another key concept is entanglement, where two or more qubits become linked, sharing the same fate. Measuring the state of the entangled qubit instantaneously reveals the state of the others, regardless of the distance separating them. Entanglement enables quantum computers to perform complex calculations in a coordinated manner. How quantum computers work. Quantum computers employ various physical systems to realize qubits, including superconducting circuits, trapped ions, and photons. These systems are carefully manipulated to control the qubits and perform quantum operations. Quantum algorithms designed to exploit superposition and entanglement are executed in these qubits to solve specific problems. So, just to note that the computer in this diagram is not all these tubes and everything is just this little part here. This is the quantum computer. The rest is just tubes that they just lower the temperature to 400 degrees Fahrenheit minus 400 degrees Fahrenheit or 0 Kelvin. So let's review the potential applications. So quantum computing has the potential in drug discovery and material science. Quantum computers can simulate molecules and materials with unprecedented accuracy, accelerating the development of new drugs and materials with desired properties. Cryptography. Quantum computers pose a threat to current encryption methods, but they also offer the potential to develop more secure quantum-resistant cryptography optimization. Many real-world problems, such as logistics and finance, involve finding the best solution for a vast number of possibilities. Quantum computers can potentially solve these optimization problems much faster than classical computers. Artificial intelligence, quantum machine learning algorithms can process and analyze massive data sets more efficiently, leading to breakthroughs in AI applications. Challenges. Despite its promise, quantum computer faces significant challenges. Building and maintaining stable qubits is a complex engineering feat. Quantum computers are highly susceptible to noise and errors, requiring sophisticated error correction techniques. Scaling up the number of qubits while maintaining their coherence is another hurdle. Nevertheless, the field of quantum computing is rapidly advancing. Researchers are actively exploring new qubit technologies, developing quantum algorithms, and building increasingly powerful quantum computers. While fault-tolerant universal quantum computer is still some years away, the progress made so far has been remarkable. Conclusion: quantum computing is a transformative technology with the potential to reshape our world. While challenges remain, the ongoing research and development efforts are paving the way for a future where quantum computers tackle problems currently intractable for classical computers. As quantum technology matures, we can expect to see groundbreaking applications emerge across various domains, ushering in a new era of scientific discovery and technological innovation. Um, so this slide has the 5 or 6 people that started quantum theory. So some of the people here is Max Planck. So here's Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. So Max Planck is considered to be the father of quantum mechanics. He proposed the energy is quantized, meaning that it can only exist in discrete units. Albert Einstein made significant contributions to the development of quantum mechanics, including his explanation of the photoelectric effect. Niels Bohr developed the Bohr model of the atom, which explained the spectral lines of the hydrogen. Werner Heisenberg developed the uncertainty principle, which states that it's impossible to know the position and the momentum of the particle with perfect accuracy. And Erwin Schrödinger developed the Schrödinger equation, which describes the wave function of a quantum system. Whew. So thank you for listening. The next session we will talk about artificial intelligence and space exploration. So stay tuned. Thank you so much.